In this lecture, we continue our discussion of series solutions of linear ODE near regular singular points. And as an example, we study the Bessel's equation. This is a general second-order linear equation which variable coefficients P, Q, and R. We can rewrite this equation in this form: x squared y double prime plus a coefficient multiply y prime plus another coefficient multiply y. Here, we assume that the coefficients of y prime and y are analytic near zero. That is to say, the xpx is a power series, and x squared qx is also a power series. This is what we say that zero is a regular singular point. Okay, so the corresponding Euler equation of our original linear equation, that is this equation, is this equation: x squared y double prime plus p0 xy prime plus q0 y. Here p0 and q0 is the zero order term in the previous power series expansion of the coefficients. Okay, that is to say, the Euler equation here is precisely the equation we considered ignoring the higher order term, because in the power series here and here we only take the terms corresponding to n equal to 0, that is p0 and q0. Okay, now to solve this equation, we consider equation of the following form. That is, y is phi r x, which is x r multiplied power series. As we know, if x equal to 0 is an ordinary point, we can try to find solutions which are analytic, that is, which is a power series. But for a singular point, if x equal to 0 is a regular singular point, in general, we could not expect analytic solution. We cannot expect solutions analytic at 0. So we multiply a singular term x to the power r. Note that here the r is not an integer. The r can be irrational even, or even negative. Therefore, when r is less than 0, this term xr will be unbounded at 0. That is what we mean the singular. Okay, so we try to find solution of this form, and to determine the coefficient an, we need to substituting this y into our equation. We have already illustrated how to find the solution of this form for a concrete explicit equation, where capital P, capital Q, capital R are given precise function. Now we are making a general discussion. Okay, so to substituting this y into the equation, because the y is the multiplication of two functions, so to compute the derivative of y will be complicated. So, but we can move the coefficient xr inside the summation, writing this in this form. Then every term in this series is only one function, not the multiplication of two functions. So this will be convenient to compute the derivative of the y. So we compute the derivative. We see that y prime is, because power series can be differentiated term by term, so y prime is the sum of the derivative of an xn plus r, which is r plus n multiply an, then xr plus n minus 1. So this is the first order derivative of y. And similarly, we compute the second order by differentiating the power series expression of y prime term by term, which gives us y double prime is r plus n minus 1, and an x r plus n minus 2. So substituting this y prime and y double prime into our Ly equal to 0, and using the power series expansion of the coefficient of y prime and q given here, given here, we can establish some relations among the coefficient of y, so that we can determine the coefficient an. This is the basic idea. So to do this computation, for example, here we have a function multiply y prime, but y prime, the coefficient of y prime and the y prime itself are all power series. So we need a Cauchy formula for multiplication of two series. If both of these two series are absolutely convergent, we have this formula. The multiplication of their sum is precisely the sum of this new series. For this new series, the nth term is aibj, is the sum of aibj, where I plus j is n. This is a formula we learned in calculus about the series. In general, this is not true, but if one of these series is absolutely convergent, then we have this formula. In particular, if both series are absolutely convergent, then this is definitely true. So absolutely convergence means that not only the series itself converge, but also the series obtaining by taking absolute value of each term, that is the absolute value of an, are also convergent. Okay, then this is called absolute convergence. So if one of these series is absolutely convergent, then we have this multiplication formula for series. Okay, so using this formula to here xpx y prime. So xpx has a power series expansion given here, and the y prime also has a power series expansion given here. So we can apply the formula to write the term in the equation into a power series. And similarly, for the term involving y, we can also do the same thing. Okay, so let's compute these two terms using power series expansion first. Okay, so xpx y prime is sum of p and xn. This is xpx. This is xpx. So y prime is this. Y prime, xy prime is this. Let's go back to have a look. So y prime, the power series expansion of y prime, the order of x is r plus n minus 1. But we have an x in front of the coefficient xpx of y prime. So the x in front of xpx will raise the order of x in the power series expansion of y prime, r plus n minus 1 by r plus n. So this gives us this term, this power series is xy prime, because for y prime the order of x is r plus n minus 1. So we have an additional x in front of the coefficients. So this raises the order to r plus n. Okay. So now for these two series, we want to apply the multiplication formula for absolutely convergent series. There is a problem. That is the xr plus n is not easy to write to consider as bn, but we can move xr in front of the multiplication first. Rewriting the multiplication in this form, then this will make it more convenient to apply the multiplication formula in the first line of this page to this multiplication. This gives us xr copy, and the new series is n from 0 to infinity. The nth order term, the nth term is ai bj. So this is the ai in the formula, and this is the bj. Therefore, this is pixi, and for the second series, replace the n by j. Therefore, we have r plus j, aj xj. So this is the result of the the term involving y prime in the equation. But we can combine the xi and xj as well as the xr in front of the summation to simplify this expression. Xi xj is xi plus j, but I plus j is n. So the final result is the xn plus r. The nth term is xn plus r. The coefficient is aj r plus j pi. I plus j summing over all ij, which I plus j equal to n. So this gives us the y prime term in the equation. Okay. Similarly, we can compute the y term, which is x squared qxy, and x squared qx is this q and xm series. And then the series expansion of y is this. Okay. I remind you that this expansion is not a power series expansion of y, because this is not a power series. For power series, the order of x should be non-negative integers, but now our r is not integers. Our r can be rational number, irrational number, and or even negative number. So y equal to this summation is not a power series expansion of y. Okay. Now, apply the multiplication formula. Here we deduce that this is the order of x. The order of for n, the x is n plus r. Just like what we did in the previous computation. And then the coefficient of xn plus r is ajqi, where I plus j is n, summing over all ij, which I plus j equal to n. Okay, so this is the series expression of y prime and y in the equation. Now, substituting all this into our equation, we obtained 0 is L phi r. Know that phi r, for phi r, what's phi r? Phi r is here. We assume that the series expansion of y, that is possibly singular function xr multiplied power series. This is the series expansion of y, and the r here is unknown, to be determined. So this r, because this function is dependent, the variable is x, but it depends on the parameter r, so we denote this function by phi rx. You can also consider this as a two variable function. The variables are x and r. Okay.